In this video, we're going to derive the differential form of the conservation of mass, also known as continuity. To do this, we are going to take a very small, in fact, an infinitesimally small cube as our control volume. We're going to look at what moves through our control volume here. So I'll draw our control volume here. So here's our control volume. It has sides of delta x, delta y, and delta z, corresponding to our coordinate system, where x is to the right, y is upwards, and z is out of the page. Now at the very center of our cube, we have some velocity, which would be given by u, v, and w. And of course the flow, or the fluid, has a density of rho. So we already know that the integral form of continuity says del by del t of the integral over the control volume of rho dv plus the integral over the control surface of rho v dot n hat dA is equal to 0. We're going to call this equation 1. And we were familiar with what this means already. This equation says that the rate at which mass in the control volume is changing plus the rate of mass outflow minus the rate of mass inflow must equal to 0. Now, for our differential form, we're first going to look at this first term here, the del by del t term. Now this term, because our element is so small, we're able to write this as, we say that this is approximately equal to del rho by del t times the volume of our cube, delta x, delta y, and delta z. So that's our equation 2, and we'll return to that in just a couple minutes. Now, so that deals with our first term for a moment. Let's look at our second term, this integral over the control surface. So next, we're looking at the rate of mass flow term. We're going to consider each dimension separately. So we'll look at x first, and then y, and then z. So this expression, rho u, what does that mean? So rho u, this is our density times our velocity in the x component. This is the x component of the mass flow rate per unit area at the cube center. So if we redraw our cube down here, we can say, okay, we have our cube face. Then in the very center of our cube, we have some value of rho u, which again is our mass flow rate per unit area at the cube center. And again, we still have our delta x, delta y, and delta z, dimensions of this cube. Now at the faces of this cube in the x direction, we're going to use a Taylor series expansion to develop expressions for what the mass flow rate per unit area might be at that face. And so we say, well, at the face, it's going to be the mass flow rate per unit area at the center, which is rho u, plus some presumed gradient, del by del x, of rho u. Rho u is going to change somewhat over the distance from the cube center to the right face, and it's going to change in the x direction. So some change per distance in x, multiplied by that distance in x, which is simply delta x over 2, or the distance from the cube center to that face. And then we can multiply that by the area here to give us the mass flow rate. So that's for the right-hand face, and on the left-hand face, we can do something similar. So we have rho u, again the mass flow rate per unit area at the center, minus del by del x of rho u. Again, rho u is changing in some way in the x direction over a distance of delta x over 2. And we can multiply that by delta y, delta z. And so for the x direction now, we can write down an expression that combines these two expressions to find the net mass flow rate in the x direction. So we'll simply we'll combine the right-hand side and the left-hand side, and what we get is this. So we have rho u plus del by del x of rho u times delta x over 2 multiplied by delta y delta z. And if we subtract out the left-hand side, rho u minus del by del x of rho u times delta x over 2, again multiplied by the area of that face, delta y delta z. Well, when we combine that and solve there, or simplify, we end up with del by del x of rho u times delta x, delta y, delta z. So that is our net mass flow rate in the x direction. Now we can work through a similar procedure for the y and the z directions, but we're not going to do that in the interest of time. We'll just say that similarly for y and z, so for the y direction, the net mass flow rate in the y direction is I of rho v delta x, delta y, delta z. And then for the z direction, we have del by del z of rho w times delta x, delta y, delta z. So if we combine the net mass flow rate for the x direction and the y direction and the z direction, we would just combine these three terms right here. So this term, and this term, and we would end up with, so this is the total net rate of mass outflow we would get del by del x of rho u plus del by del y of rho v plus del by del z of rho w, all that multiplied by the volume of this cube, delta x, delta y, delta z. And we're going to call this expression 3. And so we have expressions 1, 2, and 3, and we're going to combine those. So we're going to combine 1, 2, and 3 to find del rho by del t plus x of rho u plus del by del y of rho v plus del by del z of rho w is equal to 0. So we've simply added together essentially term 3, or equation 3, equation 2, and equation 1 just shows that those terms, when added together, are equal to 0. We've divided through by the delta x, delta y, delta z, and that gives us this expression right here, which is the continuity equation in its differential form.